Hey everybody, today we're going to talk about the Charpy impact test. This is a test that you do on materials, usually metals, to find out how much energy they absorb under an impact scenario. So if you think about hitting something with a hammer, whether that piece of material is going to dent or shatter, the Charpy impact test will give you an idea about that. So the physics of the Charpy impact energy problem is actually pretty straightforward. You start out with a little bar with a V-notch in it, and you can see that up top. And you hit it with a pendulum. Now the pendulum, it has potential energy associated with it. Mass times gravity times height. And if this pendulum were to swing freely in a perfect world, it would just end up on the opposite side of the swing and reach the same height. But if we let it impact a sample, it takes a certain amount of energy to break the sample, and in doing that, we reduce the energy associated with the pendulum. So when the pendulum breaks the sample, it swings to a lower height, mass times gravity times height, minus the energy absorbed by our test sample. So by doing this, we can characterize how much energy different materials absorb as long as we're using the same sample size. And this is really useful for finding out, roughly speaking, how tough a certain material or a certain treatment for a material is. So a lot of times we're concerned with not just how strong a material is, how much weight it can hold, but how does it respond to impacts, how does it respond to cracks and things like that. And the Charpy energy value, it gives you an idea. You can't actually design with it like you can a strength value, or there's a different type of toughness called fracture toughness. And those two you can design around, but the Charpy energy value really allows you to quickly compare different materials or different treatments. So what we're going to be doing today is looking at a steel called 17.4 pH in 3 different heat treatments. And as you can see here, the 3 different heat treatments are listed. They're called the H900 condition, H1025, and H1150 condition. And the numbers correspond to the temperature of the treatment. So 900 is 900F, 1025, 1025F, and 1150, 1150F. And you'll notice that the ultimate tensile strength and the yield strength vary quite a bit between the different heat treatments. As you increase the temperature, both the yield strength and ultimate tensile strength go down. What we'll see correspondingly is that as strength goes down, toughness goes up. So it's always important to realize that perhaps even within a given material like 17.4, a number of different treatment options are available that give you a way to strike a balance between strength and toughness. So sometimes, if you're trying to make, like, let's say a knife, you want a sharp edge, and that's generally going to require higher strength or higher hardness. So in that case, you would want something like the H900 condition. But if you're making something that's mildly structural and it needs to take a beating, you may want to consider something like the H1025 or H1150 condition, assuming weight isn't of a concern at all. The higher strengths tend to let you use less material because of strength to weight ratio, but in doing that, you're also sacrificing some toughness, or what we would also call damage tolerance. So first up, let's look at the impact toughness of 17.4 pH in the H900 condition. So the impact energy value for 17.4 pH in the H900 condition was measured to be about 25 foot-pounds in this case. And 25 foot-pounds isn't really good or bad per se. It's all about what the application requires, and it's up to the engineer to figure out what level of toughness or damage tolerance is required. And there are a couple of things to pick up on in the clip that we just watched. One is the sound that the impact makes. And if you listen to it again, you'll hear that it's kind of high-pitched, and we'll see that as the energy absorbed changes, so does the sound that's produced when the sample fractures. The other thing to notice is the appearance of the samples themselves. You notice that the fracture surfaces of the pieces that are broken open are relatively flat, and then there are these kind of ears along the edges of the sample, and those are called shear lips. and those indicate that the material was undergoing a very severe deformation in that area. And so shear lips indicate that you're absorbing a lot of energy. And generally speaking, the larger the shear lip area, the more energy you're going to be absorbing. And we'll see that as we go to the H1025 and H1150. So now we're going to look at 17.4 pH in the H1025 condition. And this condition isn't as strong as the H900 condition. The ultimate tensile strength has dropped from about 190 KSI to 155, and the yield strength has dropped from about 170 KSI to 145. But what we'll see is that the toughness has improved as a result of this change in heat treatment. So the impact energy for 17.4 pH H1025 was measured to be about 55 foot-pounds in this case. And that's about twice the energy absorbed, or more than twice the energy absorbed, as the H900 condition. But you'll notice that our strength didn't drop by half. It dropped by 20% maybe. So we didn't give up a whole ton of strength, but we gained quite a bit of toughness. And if you go back and listen to the clip again, you'll hear that the sound that the sample made when it broke was much deeper than the H900 condition sample. And likewise, when we look at the fractured surfaces of the samples, we see that the shear lips are much larger than they were in the H900 condition samples, indicating that the sample is going through much more deformation across the entire surface of the sample and is able to absorb more energy. So last but not least, we have 17.4 pH in the H1150 condition. This is going to be the softest of the standard heat treatments available for this material. The tensile strength is about 125 KSI and the yield strength is about 100 KSI. But what we'll see is that the impact toughness is substantially higher than either the H1025 or H1150 condition. So let's go ahead and give it a whack. For 17.4 pH in the H1150 condition, we measured the impact energy to be about 97 foot-pounds for these samples. So not quite double the H1025 and not quite quadruple the H900 condition. So what you can see is that you're giving up not a ton of strength to gain quite a bit of toughness as you increase the heat treatment temperature. But again, this is always based around, what are your design constraints, and so understanding what's required of the design is really important. And as far as the samples go, if we listen to the clip, we can hear that once again the sound that the impact makes is much deeper than either the H1025 or H900 conditions. And likewise, if we look at the fracture surfaces of the sample, the shear lips are much larger than either the two previous samples, indicating once again that there's more deformation and more energy absorption in these samples. So the last thing we can do once we've actually measured our Charpy impact energy values is we can plot the impact energy versus the strength of our material. And whether you're looking at the tensile strength or the yield strength in this case, we can see that as we go along the x-axis and increase our strength, the toughness drops off quite significantly. So it's really important to understand, regardless of the material you have, whether it's 17.4 pH, whether it's a typical carbon steel that you quench and temper, or whether it's an austenitic steel where you're cold working it to increase its strength, it's really important to understand the behavior of your material and how different processing and treatments affect the material properties. So in this case, we saw that as we increase the strength, we're reducing our toughness quite a bit. And this can be particularly important when we're making structures that are sensitive to cracks. So in the case of, let's say, aircraft, for example, aircraft are notorious for experiencing fatigue cracks. Making sure that a crack doesn't hit a sufficient size that a part breaks, you'd want to kind of have sufficient strength and then maximize your toughness to make sure that you're far enough away from hitting what's called the critical flaw size. But the concept of toughness is really important wherever you go. So if you happen to drop your phone on the ground and the glass doesn't shatter, the reason for that is because the glass is specifically engineered to have a certain degree of toughness to it. Or if you're hitting something with a hammer, you obviously don't want the head of the hammer to shatter, and so the head of the hammer actually has to have a good bit of impact toughness associated with it. So I hope this video was informational and instructional in understanding what is impact toughness and how it's measured, at least in metals, and how it's important for design considerations even if you can't actually design with Charpy impact values in the first place. And if anyone has any questions or comments or wants to see any other videos, feel free to put suggestions in the comments below.